we can start. And today we're happy to have Miroslav Rapcak from Berkeley, from University of California in Berkeley. The title is on the screen: W algebras and melted crystals of Donaldson-Thomas theory and Pandharipande-Thomas theory. For those who don't know what DT and PT means, so I just explained. Okay, Mira, please.
Thank you very much for the introduction, and thank you everyone for joining me. Thanks for the invitation to your seminar. First, I thought I'm going to talk about something completely different, or pretty different, some recent work of mine that would have been much more geometric. But since I was recently traveling, I didn't have enough time to actually prepare the new content, so I decided to stick with this topic from our work from last year with Davide Gaiotto, where we defined some new classes of modules for so-called W infinity algebra that I would like to introduce today, and kind of tell you the motivation for the existence of these modules and how to construct them and how they relate to the Donaldson-Thomas and Pandharipande-Thomas topological vertices. Let me start with the introduction, and since I'm a physicist, I'm going to start with a physical picture, but hopefully it's going to be understandable more or less what I'm saying. If not, feel free to stop me. I'll try to be more concrete. You can also view this part of the introduction, or basically the whole introduction, as really kind of a story, a fairy tale that is going to motivate the questions that we are going to ask in this seminar. So starting with the work of mathematicians, physicist Aldai Goto and Tachikawa, and mathematician Hiraku Nakajima, people have been investigating a rather close correspondence between four-dimensional gauge theories and two-dimensional conformal field theories. This is a rather rich subject that is often called as the AGT correspondence, or 4D 2D correspondence, or BPS CFT correspondence, depending on the authors. But all those are basically more or less the same things. One of the explicit predictions of this correspondence is equality of two quantities. One is the instanton partition function of UN gauge series, whatever they mean, computed by Nekrasov. And the other one are conformal blocks of some algebras known as WN algebras, introduced by Faddeev and Lukyanov. This is not going to be very important, the details of these objects and what the correspondence actually means, but it's important that we associate a vertex operator algebra, some kind of algebra, associative algebra with some extra structure, parameterized by one integral parameter n, corresponding to this UN, and one continuous parameter psi. I will often write psi as a ratio of other continuous parameters epsilon 2 over epsilon 1. And I will introduce this notation properly later on. It is important this correspondence can be motivated by a rather nice picture in M theory. And I would like to very briefly review this picture because it is going to serve us as a nice way to generalize the story considerably. Okay, and this picture was investigated by Nekrasov and Witten, who were looking at a stack of n M5 branes in omega background. So let me be more concrete what I mean by stack of n M5 branes.
First, maybe you should say what is an M5 brane before
yes.
you consider a stack.
Yes.
Somehow,
right.
some mathematical understanding.
Well, so I'm going to tell you what M5 branes, what M theory, and a stack of M5 branes are, roughly speaking. I'm not going to give you the mathematical definition because it's not really going to be important. The geometric picture, I mean, the kind of intuitive picture is going to be enough. But let me be at least slightly more concrete. So physicists are being interested in this 11-dimensional theory, which is called M theory. And this M theory can contain various objects. It contains two kinds of objects. It contains M5 branes and M2 branes. You can be thinking of M2 branes as 3-dimensional membranes living in the 11-dimensional space-time. And you can think about M5 branes as 6-dimensional objects living in this 11-dimensional space-time. So if our space-time of M theory is R times C4, which is real 4-dimensional object. Oh no. Okay. We can, for example, introduce an M5 brane wrapping C3 inside the C4 directions of the space-time like this. So basically, I'm just saying that there's an object, this M5 brane, it's 6-dimensional, and it lives in this 11-dimensional space-time, and I'm going to wrap it along along C3.
Sorry, I do not understand what is R cross C4. It's something 9-dimensional.
Oh,
so
sorry. It was supposed to be 5.
Okay, good.
Sorry, my bad.
Okay, and this product of 3 copies of C, it sits in the C5. Okay,
that's
good.
right. Okay. Right. And I'm going to introduce a deformation of the system by 2 parameters epsilon1 and epsilon2, associated with the torus action, the obvious torus action rotating the 2 coordinate lines inside C2. Sorry. Right. So right. Yeah, I introduced deformation. This deformation only along 2 of the directions inside the C3. And this deformation localizes. You should be thinking about turning on equivariance with respect to this torus action, and this deformation effectively localizes the theory to the origin of this C2. And such a system should admit an effective description in terms of a theory living purely on C. And the algebra of operators living on such a reduced theory turns out to be this algebra Wn, and it depends on the n, which counts the number of branes, M5 branes, supported along this C3, and 1 extra parameter that is a ratio of these epsilon parameters.
So, Miro, so for mathematicians, at least, it's just clear that there is something 11-dimensional and something 6-dimensional inside. So there are some equations here which kind of, or what, there are fields in this 11-dimensional theory which gives you the operator algebra, or what? How?
Not really. It is very hard to define. So we physicists know that this theory should exist, the theory on M5 branes, but we don't really know what it is. We don't have like very precise definition. We often know what it compactifies to. If you, I mean, we know. We have quite a lot of hints about the what M5 branes are.
Yes, but when you say that there is some algebra, because you will be talking about where it comes from. So far, it was geometry, 6
exactly.
and 11. Yeah.
So you should be thinking about all the branes to be effectively described at low energies, but some kind of quantum field theory living on its support. This basically describes how like the small fluctuations of the M5 branes in the 11-dimensional space-time and other degrees of freedom. But now if you turn on this deformation, this omega deformation, by these epsilon parameters. Some of the degrees of freedom of the M5 brane get frozen, and the theory effectively localizes to theory living only on the C, not on the full support of the brane, but only on the C itself. And yeah.
Okay. No, I mean, to think about these parameters, should I think like about some functions on some space, and then this epsilon1, epsilon2 quantize these algebra functions, on how mathematicians can think?
Right. So this is what we are going to see in the case of M2 branes.
Okay, not M5 but M2.
Not really here.
Okay.
I'm just thinking if there exists such a. Well, you should really think about the epsilons as being the equivariant parameters for some for the torus action U1. But you can indeed also like in the case of M2 branes, we are really going to see that these are going to play the role of deformation of some functions on some variety.
Okay, but not for M5. Okay.
Not for M5.
And can you just tell for ignorant mathematicians why there are only M2 and M5 and not like something else, M7? Is it just because of some equations, or what's the prohibition law?
Right. So the first questions you need to ask when you're formulating string theory, you need to ask what are the supersymmetric modes of the strings, and those turn out to be in correspondence with well, let me say it differently. It turns out that those are enough in order to be able to reproduce, engineer all the branes in type 2b and type 2a string theory from the compactification of M theory.
On what? On the circle or on the line?
On a circle.
Okay, so this is 11-dimensional, and the string theory lives in 10 dimensions, so you compactify, and M5 and M2, this 5 and 2, which means 6 and 3 dimensions, it's enough to produce all possible types of branes in the string theory in 10 dimensions. Okay.
Right. So this is kind of roughly speaking how that works. So you don't need anything else. And also,
can I interrupt? For more ignorant mathematicians, what are the differences of M5 and M2?
What are what?
What are the differences of M5 and M2?
Dimension. M5 branes.
5. Okay.
M5 branes are 6-dimensional, and M2 branes are M2 branes are 3-dimensional.
And what will be the dimension of M3?
Well, there's no M3 in M theory, but if we are in string theory, there would be something called D3, and the dimension would be 4. So basically, the reason is that the space-time in physics consists of time and space. Okay. In our usual world, we have 3 spatial dimension and 1 time dimension. In string theory, you can have more spatial dimension, but you always have the time dimension.
Okay.
And physicists basically just always label higher dimensional objects or something by their space dimension. So you say that particle is 1-dimensional object in space, but sorry, 0-dimensional object in space, but 1-dimensional object in space-time.
Thank you.
No problem. Okay, so to give you an example of these WN algebras, W1 is nothing else but the universal enveloping algebra of the algebra generated by Jm and Jn and satisfying the following commutation relation. And this picture, we won't really need details of this picture. We won't really need to know what exactly the M5 brain, the branes are. It is really just enough to know that there are these higher dimensional extended objects. You can place them on each other, you can intersect them, and so on. But having this in mind is going to lead us to a pretty nice generalizations of these algebra Wn and their modules and so on. So that's why
how you will intersect 2m5 if you do not allow all possible, what's the dimension of the intersection of 2m5s? It's like 2 6-dimensional objects in 11-dimensional, so their intersection is 1-dimensional.
Well, it very much depends how you intersect them. We are going to see.
They do not have to be transversal, but they can be.
Yeah, that's right. That's right. I'm going to be like very specific on the next slide about what kind of configurations I allow. I will be pretty general, but not.
And you need this equivariancy in order to get something which sits on C. It's a something holomorphic, so your algebra is indeed the vertex algebra or some, W.
Exactly. That's right. Yeah. Right. This is usually like how physicists motivate this whole AGT story and all that, like from this compactification of M5 brains. And yeah, that's right. But you can actually, I think, well, anyway, let me not make this comment at this point. Okay, so now I told you a pretty old story with M5 brains. You can do the very same discussion of with M2 brains. So in particular, there exists an analogous story for a stack of n M2 brains living on R times C epsilon 1, leading to one parametric family of algebras AN, quantizing the ring of holomorphic functions on the ADHM quiver variety, where n is the rank associated with the gauge node. So I'm looking at the moduli of representations of the following associated with the ADHM quiver with these dimensions. And again, to give you an example, the simplest algebra A1 is nothing else but the universal enveloping algebra of the standard Heisenberg algebra generated by the derivative and Z.
Mira, I'm confused a bit at this point because this quiver which you wrote down, so it should be familiar at least to my graduate students. Yeah. Anyway, you are talking about quantization of algebra of holomorphic functions, and this is Hilbert's scheme.
Yes.
Because you put one, but there is a problem with holomorphic functions. You see what kind of holomorphic functions it's.
So what is the problem with the holomorphic functions?
No, you should specify, because it's if you restrict them too much, you don't have any. If you do not restrict the behavior, maybe you have more than you want, then you are able to quantize.
Yeah.
Are they just like what you wrote, that it's regular functions like traces of products of these loops?
Right.
Okay.
So these are exactly the things that I do. I quotient by the right ideal generated by the relation B1, B2 equals IJ or JI. And I introduce commutation relation B1, B2 equals epsilon 1 and IJ equals epsilon 1 up to some delta. I mean, so I have to identity. So
this is a quantization of this.
This is exactly. So this is what I mean by quantization of the holomorphic function. Okay.
The quiver you wrote is that's for A1, right? With one single vertex. Okay, thank you. So AN where you have N vertices.
No, you mean A1 for
no AN.
Yes. For A, yeah, that's right.
AN. N is a charge of the instanton, yeah.
Right, that's right.
Okay.
N is charge of like the N here. The N here is charge of the instanton here. So
okay,
right.
So in particular, N quiver.
No. So the n here, an here, is the n specifying that bi is a map from Cn to Cn.
I see. Okay, so that's the dimension.
And for higher rank instantons, is there a problem?
There will be different algebras that, I mean, that I don't know much about. Well, actually, no. So you can do higher rank, and you would get kind of a matrix generalization of the story, because there you have also operators of the form AK, AK, A. Sorry. B1, 2, B, C, J, I, C. Like these kind of marginal operators. And that would lead like to a matrix generalization. So this leads to something like some like, yeah, right.
Okay. All right.
Okay. Yeah. So basically, I just wanted to introduce these M5 brane algebra, like M5 brane and M2 brane algebras associated with stacks of M5 branes and M2 branes. And now we are going to move to the generalization. So as I told you, M theory is 11-dimensional theory, and we have quite a lot of freedom to play around with these dimensions. The first modification we are going to make is, instead of compactification on this C squared, where by compactification I mean turning on this omega deformation parameterized by epsilon1 and epsilon2, I'm going to compactify on C3 and then turn on equivariance associated with the free torus rotating the different C's. And we are going to now study different branes in such a geometry by not changing anything in the non-compact part. So I will call this part non-compact and this part compact. And and the crosses in the table show the support of the corresponding brane. So in particular, in M5 branes, before we had this one C, and we had two C's in the omega deformed direction in the compact part of the space-time. So what we are going to do now, we are going to we can obviously modify this picture slightly by keeping the same support in the non-compact part of the space-time, but considering the three possible orientations in the compact part of the space-time.
Mira, I'm confused because in the case which you explained, like only two parameters are present, you said that the answer depends only on one continuous parameter, which is a quotient of them. Is
right.
it the same for these three-dimensional torus, that in fact only two parameters are relevant? So
it actually turns out that only one parameter is going to be relevant, because there one needs to impose one extra condition that epsilon1 plus epsilon2 plus epsilon3 equals 0.
Yeah, it's Calabi-Yau condition.
Is this the Calabi-Yau condition? That's right. That the torus action preserves the like Calabi-Yau volume form, and it turns out that the actual algebra in the end is invariant under rescaling of all the parameters.
Okay, so instead of two, you have one.
That's right.
Right.
So again, the resulting algebra is going to depend on a single ratio that I can pick, for example, epsilon1 over epsilon2. Okay. And we can do the very same thing with the M2 branes, wrapping the same R in the non-compact part of the space-time and wrapping one of the C's in the compact part. Okay. And the very same argument that people usually use for the physical motivation for the AGT correspondence, or this for the 2D correspondence, now leads us to a prediction that there should exist a free parametric family of algebras that I denote as W, N1, N2, N3, associated with the general configuration of M fibranes, where I consider N1 M fibranes with one orientation, intersecting N2 M fibranes of the other one, and N3 M fibranes of the third possible orientation. And analogously, you can define algebras associated with the general configuration of the M2 branes, leading to free parametric generalization of the algebra that quantizes the holomorphic functions on the ADHM.
Miro, may I interrupt you here? I see some discrepancy because for M5 branes, you're talking about vertex operator algebras, but for M2 is just associative algebras.
Yes.
So is it really like that?
It is, and it does have a reason, because vertex operator algebras are always associated to some holomorphic dependence. You need to have some kind of holomorphic dependence on position. And indeed, from M5 branes, these extra directions in the non-compact part of the space-time, we did have a holomorphic dependence on the position in C. But for the M2 branes, you don't have such a dependence.
I see.
So you still do expect to have some kind of algebra of operators, but you don't expect any holomorphic dependence.
And so this R is one-dimensional support. And so it's kind of line operators somewhere.
Exactly, that's right. So you can that's right. That's a very useful picture. So if you compactify on this part of the space-time, you still have some you still have a kind of effective five-dimensional theory along R, C, and C. And in this five-dimensional effective reduction of M theory, there will be the M2 branes are going to lead to line operator along the R direction, and M5 branes are going to lead to a surface operator along one of the C's.
Okay. All right.
Right. That's right. Okay. And for the purpose of our talk, it is actually useful to think about these W, N1, N2, N3, and A, N1, N2, N3 as a quotients of some universal algebras that I denote as W infinity and A infinity. And this is actually what we are going to need. I could have defined for you what this general A, N1, N2, N3, and W, N1, N2, N3 is, but we wouldn't get to what I'm planning to talk about today. So we are really going to talk about these universal algebras. But before introducing those universal algebras, and I'll try to do it pretty explicitly, let me discuss one more generalization and investigate endpoints of M2 branes on M5 branes. So from the picture here, you can really see that, or let me redraw the picture. So from the point of view of the non-compact directions, as I've just stated, the M5 branes are supported on C, on some surface C inside inside the non-compact part of the space-time, and we can look at M2 branes ending on the M5 brane as follows. And you can see that from the point of view of the theory of on the M5 brane, the endpoint is going to give rise to some kind of operator in the M5 brane theory. And you can look at a fusion of local operators on M5 brane with this endpoint. So this kind of motivates an existence of a module for the M5 brane algebra, W, N1, N2, N3, associated with M2 brane endpoints on the N5 brane.
And algebra should correspond to zero-dimensional objects mathematically, or what? Because why
yes,
not the other way around?
that's right.
Yeah, okay.
That's right.
So this picture with red arrow means that your your vertex operator algebra, yeah, it should have some representations associated with a particular M2. With
Exactly.
fixed. Yeah, okay.
Exactly. And there's extra data of a partition that tells you how exactly the M2 branes are distributed on the M5 branes. If there's more of them, you need to specify which M2 brane exactly acts ends on which M2 brane, and this leads to the requirement that this endpoint is actually parameterized by partition. And these partitions are free because there are three different orientations of M2 brane. So this is kind of a picture that motivates an existence of a module for the M5 brane algebra, parameterized by a triple of partitions. But analogously, viewing the very same system from the perspective of the M2 brane algebras, the very same endpoint should lead to a module for this M2 brane algebra A, N1, N2, N3, again labeled by the triple of partitions lambda mu nu. And
what you said that it's like three orientations. How do we see them?
So those are the three orientations from the previous slide here.
Because there are different.
One, two,
there are
three.
different number. Okay, good. All right.
Okay. So the question, what are these modules, is one of the main questions we ask in the paper with Davide from last year. And today I'm going to tell you what are these modules at the level of these universal algebras, as I promised. And along the way, we are going to see quite a lot of interesting things. For example, the character of the W infinity modules turn out to count melted crystal configurations of the Donaldson-Thomas topological vertex. Characters of this A infinity modules count melted crystal configurations of the Pandharipande-Thomas topological vertex. I will introduce both later on. I just here want to state briefly the results that we are going to see. Then we are going to see that the DT-PT correspondence relating the topological vertices in the following way actually has an algebraic uplift. And we are going to see that in defining explicitly the PT-like modules, we will need to introduce some new techniques for affine in the representation theory of affine Yangians by, for example, allowing non-diagonalizable action of its Cartan generators. Okay. So let me just briefly tell you what W infinity algebra is. And then we'll anyway switch to the algebra of its modes that is isomorphic to the affine Yangian of GL1. So this section 2.1 is not going to be that important, but it is still going to motivate one important element of our analysis. So W infinity algebra plays an important role in many places in physics and mathematics, and in particular in our story, it is the universal algebra describing M2 brane algebras W, N1, N2, N3 that can be thought of as their different quotients. Right. So we will actually these the W algebras form actually a richer structure called vertex operator algebra. This structure is not going to be very important for the analysis of these modules, but let me at least tell you a little bit and sketch the definition, or kind of tell you the easiest way how to define this W infinity algebra. So vertex operator algebras contain are generated by so-called vertex operators, and you can be thinking about vertex operators as formal series of some ordinary operators acting on some vector space, of the following form. Roughly of the following form. Let me add 2 here for some reason. And the relations of the algebras are encoded in so-called operator product expansion. There are expression of the following form. You can deduce the commutation relations of the modes of the modes by doing some contour integrals on the right-hand side of the expressions here. But this is not going to be very important. What is important that there's, for example, like one of the standard examples of vertex operator algebras is the Virasoro algebra, generated by single field T with the following OPE, depending on central parameter C. That is called central charge. Anyway, there's this vertex operator algebra. Let me also define a primary field. Primary field is a vertex operator, the Wn, with the following OPE, operator product expansion, with the stress with the Virasoro algebra. And the spin n appears here as a prefactor in the second order pole. It turns out that there exists a 2-parametric family of vertex operator algebras W infinity, extending the Virasoro algebra by primary field of spin 1, 3, and 4. This was first suggested by Gabriel Gopakumar and proven in the recent work of Linshaw. And in particular, all the relations of the algebras can be obtained via so-called bootstrap procedure by imposing associativity of operator product expansion. So it turns out if you take algebra of generated by these fields that I just taught you and try to impose the associativity of OPE, operator product expansion, it just turns out that there are only 2 free parameters that cannot be fixed. But unfortunately, to do this analysis explicitly is very tedious and hard. But luckily, the mode algebra of these W infinity algebra is isomorphic to another algebra with a rather concrete description. And this algebra is known as the affine Yangian of GL1.
Mira, I'm kind of sorry for being too pedantic, but affine Yangian, it's an associative algebra,
Yes.
and W infinity is a vertex operator algebra. So are you talking about some associative algebra which you assign to your vertex operator algebra or what?
Right. So to each vertex operator algebra, you can associate an associative algebra of its modes. So basically what I take, I look at all the, I really look at the associative algebra generated by these LNs. So I'm forgetting a lot about the VOA structure.
Is it just a universal enveloping algebra of Virasoro?
Yes.
Okay.
In the case of the Virasoro algebra, where the Virasoro algebra would be the algebra that I called W2.
Yeah. Okay. Okay.
W infinity would be something bigger.
Yeah. It's sort of like algebra of differential operators on the circle or something.
Yes, but it's double quantization.
Yeah.
But exactly, you're right. Yeah, so W infinity is 2-parametric deformation of the universal enveloping algebra of the things that look like Z to Z to the what did I do? Okay, Z to the n del to the m over m is greater or equal to 0 and n is any integer. Okay, right. So this is W infinity algebra. And Jan, thank you for the comment. That would have been probably the easiest way to introduce W infinity. Okay. Right. Now, what is going to be quite important from about from the theory of these Wn and W infinity algebras is that W infinity admits a very simple automorphism. It simply changes the sign of some of its generators in a very simple way, given by the following formula. And even though this is actually very trivial automorphisms, and it has been overlooked very much in the VOA literature because it doesn't really do very much. But we are going to see that if we translate this automorphism into the language of affine Yangian, this is going to lead to pretty non-trivial predictions. It's, for example, going to relate modules with the standard nice action of Cartan generators with modules on which the Cartan generators act by a non-trivial Jordan blocks.
Is the Wn here the modes of the vertex operator?
These Wn? Or, no, these are the, so you should think about Wn as, I should have written Wnz, I guess, to be more precise. So Wnz is sum over m going from minus infinity to infinity, Wn m z m plus n.
Plus m.
There's a reason for like these shifts. It's not very important, but like remember here for the W2.
Yeah, you take the derivative.
I introduced this 2 here, so this is like consistent. It's not very important, and you can really just relabel them. It's just convenient. This is what people usually do.
Yeah.
But anyway, not that important. Thank you. Right. So now knowing that the algebra is as an associative algebra that is isomorphic to the affine Yangian, let me write down explicitly the relations of the affine Yangian. They are pretty complicated looking, kind of ugly, but the important fact is that you can really write them down very explicitly compared to the relations of the W infinity itself. One comment, one remark that I want to make at this point is that you should be thinking about E's as raising generators of the algebra, F's as lowering generators, and psi as Cartan generators. And also that the algebra depends on 2 continuous parameters, sigma 3 and sigma 2. There are the following combinations of the epsilons introduced above. Okay. Now we're at a position where I can very easily define this A infinity algebra in terms of a subalgebra of this affine Yangian of GL1. This A infinity algebra is sometimes also called one-shifted affine Yangian or double affine Hecke algebra, and is generated by Fn and psi m n for arbitrary non-negative integer n, but for En restricted to n going from 1 to infinity. This is rather simple algebra, but rather simple algebra to define once we have this affine Yangian picture. Okay, and this A infinity algebra turns out to be the universal algebra describing the M2 brane algebras A, N1, N2, N3. This was shown like
universal means that for fixed N1, N2, and 3, it's a quotient of A infinity.
Exactly. Exactly. That's right. So this was proven for the N00 case in Kodera Nakajima, maybe somewhere else as well, but it's surely there. And in the general case in the work with Davide from last year. Okay, But since I haven't told you what A, N1, N2, N3 is, then I cannot be more precise about this statement. Okay, so let me also write down explicitly the isomorphism between the affine Yangian and W infinity. And for that, let me define slightly different generators of the GL1 affine Yangian by writing the following commutators, successive commutators of F1 with F0, E1 with E0, and the following commutation of E1 with E2. I mean, you can just believe me that this is an isomorphism of this expression gives an isomorphism of associative algebras. Okay, but what is important, and in this Yangian basis, the charge conjugation automorphism is not that simple anymore. It acts simply on the generators J, but it transforms H in the following way. In particular, we get this tail term that leads to many interesting, that has many interesting consequences. And the appearance of the tail in the second, right. And as we are going to see below, this charge conjugation automorphism relates well-known modules of the affine Yangian with rather exotic modules with non-diagonalizable action of Cartan generators. Okay, but before moving to the discussion of the representation theory of our algebras, let me rewrite the algebra relations and the algebra slightly differently by introducing yet another formal generating series of the following form. Using these generating series, you can write down the relations of this GL1 affine Yangian in the following slightly more compact form, where I introduce the following ratio, the following ratio. How you should be thinking about the relations. You should be thinking about them as encoding all the relations from the previous slide by first multiplying by the denominator of phi on the right hand side of each of the relations, and then expanding around infinity in both Z and W, and identifying the coefficients on the right and left hand side give exactly all the relations above. Okay, so now we are at a position to define the modules, the DT modules, the PT modules, and try to understand the relation between them. It has been known for quite some time that this W infinity algebra admits a class of modules M lambda mu nu parameterized by a triple of partitions. The trivial case where all the partitions are trivial was introduced, I think, first in the work of Feigin, Jimbo, Miwa, and Mukin in 2012, and constructed geometrically using homological algebra in our work with Jan Yaping and Gufang from last year. And generalization with arbitrary free partitions was proposed, I think, for the first time in the work of Tomáš Procházka, and we relate them to the system of M5 and M2 branes in our work with Davide. And to define M lambda mu nu, I first need to introduce a basis of the module that is labeled by 3D partitions built on top of so-called vacuum configuration. So let me tell you what a vacuum configuration is. Vacuum configuration is a 3D partition that asymptotes to free prescribed Young diagrams. So for example, here I'm writing down the vacuum configuration for M box to one partition and one. And these are exactly the asymptotics along the free coordinate lines here. So this would be the vacuum configuration. And the excited states, or other states of the modules, are then associated with the various box configurations with the same asymptotics. So for example, in this case of 0 box 0 module, we have the vacuum configuration. There are two different ways how we can add single box on top of the vacuum configuration. And we have these different configurations at weight 2. Okay, so now I told you how the module looks like as a vector space. It's labeled by these 3D partitions. And now let me tell you how the generators of the affine Yangian act. So first, the above basis diagonalizes the action of the generating function psi z. And I'm going to write down all the relations at the level of generating functions. If you want to know how the different psi I, ei, and fi act, you have to expand around infinity and identify the corresponding coefficients. So the action of psi is given by a product of these factor phi shifted by epsilon box for each box at a position x1, x2, x3, where the epsilon box is given by the following combination of epsilons. And all that is multiplied by extra factor of the following form. Similarly, EZ acts as a raising operator, adding boxes at each allowed location. And FZ acts as a lowering generator, removing boxes at each allowed location. To be more concrete, E of Z acting on a vector associated with some partition is going to contain a bunch of terms. Each term corresponding to one configuration that can be added to the original configuration lambda, so with the corresponding state of the following form. There is a factor 1 over z with the residue at the position of the added box, this epsilon box, and there's some extra factor proportional to the residue of the side generating function acting on the original vector. So in our example, where we have a single asymptotic 0 box 0, we have the vacuum factor, and we have sum over all the boxes in the vacuum configuration, right? So there's infinitely many of them here. It turns out that there's a lot of cancellations, and the final expression has the following simple form. Expanding in modes around z equals infinity, we can identify the action of psi 0, psi 1, psi 2, and so on. Similarly, EZ acts as a raising operator. So starting with the vacuum configuration, we get sum of two states by action of E, proportional to 1 over z minus epsilon 1, because the position of the first added box is at 1, 0, 0, or here 0, 0, 3, 0, 0, 1. And there is this extra numerical factor E1 and E0 that is the square root of the residue. And one can write down an analogous expression for the F generators as well.
So just let me go back to the, you are adding the boxes in the direction of the E1, E2, E3 in those three directions, am I right?
Here? There are not three directions. Remember here. So this was this.
You have a 3D. You can add boxes in 3 different directions in 3D place, right?
Well, if you have empty configuration, like this one, you can add. You have a single configuration with one box, two configuration and 3 different configurations with. With 2 boxes, this one and this one. But the example that I was talking about was a non-trivial one. It was the one associated with the 0 box 0. So it means that we have an infinite row of boxes here. And the only way how to add a single box is to either add it here or to add it here. There is no other way how you can
Or the
add.
other direction is infinite. There is no place to add.
Exactly.
Okay.
That's right. That's exactly the reason. Okay. The seminar is usually 1 hour, right?
Well, you can go over the time if you need. Yeah, it's kind of too many questions.
No, that's fine. Okay. I will skip some parts, but I will probably go over time, maybe 10 minutes, if that's fine.
Yeah, that's fine.
Okay. Because I'm going really much slower than I thought. Okay, but it's great. It's always better to have many questions than not have any. So continue asking. Yeah. So let me recall that we had the charge conjugation automorphism, sigma, and let me also label by this notation lambda mu nu, the lowest weight vector of the module m lambda mu nu. Recall also that we had an embedding of this A infinity in W infinity for getting the generator E0. So the surprising observation that was quite surprising for us actually is that acting by the generators of this A infinity subalgebra on the highest weight state M, lowest weight state lambda mu nu via conjugation generates a lowest weight module of A infinity. And it turns out that the character of this module is given by the Pandharipande-Thomas topological vertex. Pandharipande-Thomas topological vertex. And in the rest of the talk, I'm going to sketch the idea of the proof of this statement and offer a more concrete definition of such modules by utilizing Pandharipande-Thomas box counting.
Yeah, but Miro, how you kind of separate DT from PT? How do you know that these are PT modules and those DT modules? You have just three-dimensional partitions, which gives you some basis and so on, so on. How?
Right.
Of course, in the end, you can look at the characters and see something, but why you call them in this way at the very beginning?
Okay. Well, at this point, it is not obvious. It is really obvious from the form of the partition. But basically, if you were to ask the question, what are the generating function for DT and PT invariants on Torri-Calabi of free folds? They would be you can write them in terms of sum over products of some factors that are called topological vertices. And people know what these topological vertices are that give the correct counting in the PT and non-commutative DT chamber. And if you were to compute the characters, it just turns out that these modules have the correct characters to identify them with these objects. Very likely, these modules actually have a geometric construction where you can really explicitly see the relation to DT respective PT invariants, but it's not clear to me at the moment.
Yeah.
So,
okay.
So far it's really at the level of characters agreeing with something that gives the PT versus non-commutative DT invariants on toric free folds.
Okay.
Okay. Right. So let's see. That is important. Okay, so let me just go very quickly. Well, I could maybe skip this one. Right. So this is kind of maybe important. Yeah, it would just take way too long to make this argument, but I think I need to do it very fast. So okay, so the simplest example of a single asymptotics was investigated in the work by Gabrielli and Peng, and they found out that the box counting in these conjugate modules is done by counting boxes at two different locations. One is the DT location, which gives just the counting of the standard partition with trivial asymptotics, and the other one I will call high wall location. I will call it the PT location. And the PT location, the counting at the PT location is slightly different compared to the DT location. It counts boxes that can be removed from the vacuum configuration that has the following form. So you take a vacuum configuration going in the infinite direction along one of the axes, and having a prescribed shape. And now you take and you start removing boxes out of this configuration. So at level 1, you can remove this box or this box. At level 2, you can remove either these two boxes, or this box and this box. And what we have done with Davide, we have argued that this picture of two independent locations actually persists also in the general case of M of the conjugate modules associated with the M, mu, nu, and lambda. I want to sketch the proof, but since I already ran out of time, let me just skip it. But the whole consequence of this argument is that the character of this conjugate module that actually equals the character of the non-conjugated module, because the generator that counts the number of boxes is independent of this charge conjugation, is given by two factors. One factor, the McMahon function, that counts the standard 3D partitions, and another factor that I denote as chi pt lambda mu nu, count boxes at this pt location. But this is exactly the formula rating the DT and PT topological vertex from the work of Pandharipande-Thomas. Let me now tell you that there actually exists a way how to naturally divide by the McMahon part of M tilde at the level of algebras. Assuming that EZ acts again as a sum of terms proportional to 1 over Z minus epsilon box, where epsilon box is the position of the added box. Addition of the first box at the DT location must be of the following form, plus some dots that do not contain boxes that are not added at the DT location. So the first box at the DT location can be thus generated only by E0. So restricting to the co-kernel of E0 produces a nice module for the subalgebra A, generated by all psi I and fi, for I going from 0 to infinity, but EI restricted to the positive integers. So we can see an algebraic uplift of the relation between DT and PT topological vertex as the PT module being a co-kernel of E0 acting on the conjugated DT module. Okay, and in the rest of the talk, I wanted to actually offer you a more concrete definition of these PT modules, but since I don't have enough time, I'm going to skip it and just tell you the result. In order to give an explicit definition of the of the PT modules, I would first need to tell you how the addition of boxes at PT location look like for the general configuration of the free asymptotics, and then try to write down the action of E, F, and psi generators. It turns out that this can be consistently done only by introducing higher order poles in Z in the action of E. So you can see that there are going to be different kind of states associated with the first order and second order pole compared to the previous DT module story. And actually it turns out that the generator psi does not act, cannot be diagonalized anymore. And we get these non-trivial Jordan blocks. So I'm missing something here. This should be multiplied by lambda box L. So you can see that these kind of extra terms lead to the non-diagonalizable action of the generator psi. Right. So here are roughly all the relations, how they look like in the general PT module. Yeah, so in summary, we have seen that the trivially looking charge conjugation automorphism of W infinity has highly non-trivial consequences when used in the context of the affine Yangian. We had found a pair of A infinity and W infinity modules parameterized by partitions lambda mu nu describing endpoints of M2 branes on M5 branes from the perspective of either M5 brane or M2 brane. And we have seen, or I've told you, that their character coincides with the DT topological vertex and the PT topological vertex. Furthermore, PT modules admit an explicit construction utilizing Pandharipande-Thomas box counting, but they require an introduction of non-diagonalizable action of Cartan generators and higher order poles in generating functions. Unfortunately, I had to rush through this part of the talk, but
yeah, but this non-diagonalizability sort of Jordan block, is it infinite or it's kind of ends up? It's kind of if I subtract diagonal part, will it be nilpotent of finite order?
Yes. So basically, you get at so still the Jordan block is going to be of the size smaller than the dimension of the let's see. Right. So the action of psi is going to be decomposed in blocks of size given by the number of boxes of number of configurations with a given number of boxes. Am I saying it clearly?
No.
I thought so. Yes. So the short answer is that no, you're always going to get blocks that are of finite type.
Yeah.
That's a logarithmic module.
Hmm?
Can you say it again?
Is that the logarithmic module?
Yeah.
Okay.
Yeah, but you see, so kind of
generalized eigenspace is still finite dimension. That's what Yang is asking.
Yeah, but it's kind of I asked that question because I mean it's nice formulas, but certainly there should be a geometric construction of the this kind of box counting, it's of course it's just a realization of certain geometric construction in the basis of fixed points and in the cohomology of the moduli space of certain sheaves. Similarly, well, similarly to what we did with quivers, but it's even better if you don't have quivers. Now the nilpotency can be a sign that you have non-reduced subschemes. It's like, that's what we discussed. So there are two types of modules. One which we constructed with Gufang and Yaping, and the other one which we constructed with Diaconescu and others in the simplest case. And with Emmanuel, what we did, we consider a non-reduced divisor, like you take the coordinate plane, C square, but impose the condition that this third coordinate set z equals 0. This is my, I take the equation z in the power whatever, like 50 equal to 0. So now it's a non-reduced divisor, and I consider, at least we considered, sort of Hilbert scheme of this divisor, which is absolutely not clear how to do if you have like configuration of 3 or even 2. But if you consider such things, then this nilpotency, finite nilpotency in one direction, it should kind of, maybe should, or at least can, it's an opportunity to give rise to certain finite type of nilpotency for the action, for the operators acting on it. I don't know. At least this is indeed, this is mysterious. This non-diagonalizability, it's something which I did not.
So first, I do not expect this non-diagonalizability to appear when you're looking at like things that look like quad schemes of these non-reduced divisors, but rather something that is codimension 2.
Okay.
Object.
All right. It's not. Yes. Of course, it's not C square. It's just C. It's a line.
Right. So these kind of things. I mean, yeah, this is kind of the prediction. But you're saying basically that if you consider these non-reduced schemes, you can see a way how this non-diagonalizable action appears somehow naturally.
No, I think it's kind of this question about, it's a question about the geometric construction of these modules and the algebras. It's overdue. I mean, because it's kind of it is needed everywhere, and not only in our story, but in this Nekrasov story, in the full dimension 4 for Calabi-Yau fourfolds, when instead of Koha you consider its generalized version, what Nikita calls as mama algebra, something like that. It's and representations of, so then, but there is no geometric construction, so which is very pity. So it's kind of, it's unsatisfactory, and so it's nice formulas, but why? But anyway, so
though I do have a hope that making things work, at least in this example, might be easier than the 4D story that you are mentioning.
Yeah. But even in this case, why? What is geometric construct? Even in our paper with Yaping and Gufang, what's a geometric construction of the stable representations of quivers with potential? It's kind of, yeah. Because your formula for the relation between two characters, which you algebraically upgraded on your slide, let me go, on this page 29, this DT-PT correspondence, it's algebraic. It's a general fact, because at the level of characters, you always obtain the PT generating function defined geometrically. Even for not necessarily, I believe, toric Calabi or threefolds, by dividing the generating function for DT invariants, but certain power of McMahon, like Euler characteristic of your threefold. Right. So this is very general. So yeah, so then this, of course, this algebraic upgrade of this last line, it should be true always. It's certainly have a geometric nature.
Yeah, I totally agree. I totally agree.
So yeah, so it's kind of, there should be geometric counterpart of your work, and probably since it all comes from first from W infinity, yeah, so then it's certainly related to cohomological whole algebra of whatever of C cube. Yeah. It's really nice. Yeah.
Thank you.
Yeah, okay. There is also last page. Slide.
It's just an outlook.
Yeah, geometric with what I just said. Updates hopefully soon. Yeah. Okay. You work with Batson on that. Yeah. Okay. Good. Do you? Yeah.
Like with Dylan, we actually are trying to work out the the brains on spectral sequences and these kind of things, and try to give the geometric interpretation of these moduli spaces. But we still don't have full story, I feel. So
yeah, and the last 4 authors, it's outgoing. Yeah. Yeah. All right, and also kind of some program. Yeah, rich classes. QD form, what means QD forms? You have plenty of parameters, epsilon1, epsilon 2.
So this is kind of the K-theory versus
okay. All right.
cohomology. But that seems to be somehow complicated in the M2 brain algebras, because these modules don't seem to, like the QD-form version don't seem to admit highest weight, like natural highest weight modules. So I'm a bit puzzled by some of the generalization to the QD-form version on the M2 brain side. There are a bunch of puzzling things.
Yes. Of course, if you have a geometric description in terms of this cohomology of the moduli space, you just replace it by K-theory and everything should work. Yes. And also, you mentioned Kadera Nakajima at the beginning of your talk, and also you mentioned some possible relation to the Coulomb branches. So what's the status of that story? Right. Do you still believe in it?
Yeah, I'm at the moment, I'm actually not that optimistic about the relation to the Coulomb branch story. The reason why it works for the simplest example for the AN algebras. So for these the algebras that I call AN or AN00. I told you that those can be viewed as the quantization of functions on the ADHM, and I would call this description the Higgs branch algebra. But in this very simple, in this class of examples, this theory is a 3D mirror to itself.
Yeah, because the Hilbert scheme is self-mirror. Yeah.
And the mirror symmetry, the 3D mirror symmetry switches the Higgs branch and Coulomb branch algebras. So these algebras A and have an alternative description as a Coulomb branch algebra for the very same quiver. These just give the same algebras. But this really seems to be just a coincidence, probably, of the example at hand. Yeah.
Hold on, but if you consider three different, like N1, N2, and 3, so well, you know what you should do with this Nakajima quiver. Yeah.
No, I don't know, and
Why?
neither of the two descriptions. I just don't know.
I'm confused. You told at the very beginning that you take this moduli space, in this case of Hilbert schemes, and then you take algebra of holomorphic functions, and then you quantize it somehow. All right, now you have N1, N2, and 3. Why you cannot take I remember you tried to do this. First quiver with 3 different framing vertices, which you kind of glue together. I can yeah.
You mean glue by the framing vertex, something like?
Yes, something like, yeah, I remember you mentioned something like that. But first you start with, yeah, with something like this. Yeah, with a potential, probably. Anyway, to construct this sort of a generalization of Nakajima moduli space, take functions on this moduli space, quantize it. Then you have Higgs branch, and whatever will be mirror, I don't know, but probably it's computable.
Maybe, yeah. Maybe. Yeah. So, do you know what would be the relations? Do you know?
Well, I would look for the potential. So
the potential.
Yeah, the potential. There are plenty of possibilities. I hope that it should be kind of similar to the potential which we considered, but in a slightly different. You remember in different framework. At least I would kind of try to guess.
Okay, I can try to do some guesswork. Maybe.
Yeah. All right.
That'd be great.
Yeah.
Yeah. The way how we define these algebras with Davide is really by utilizing the coproduct.
No, maybe you should say it. I looked at the paper, but I remember you had some coproducts on this algebra, some generalized. I don't know.
Well, actually, I think it's much better to. Okay, let me here and.
Yeah, just okay, good.
Oh, what have I done? Okay. Right. So it is better to like for this construction. It is better to okay. So let me now tell you what are the A00, A100, A010, and A001. So these are representations of the A infinity algebra given by, I introduce these generator Jn, and this one gets mapped to 1 over epsilon 1 Zn, and I had this other generator T that maps to the epsilon 1, the second derivative of Z, and analogously for the other ones, with the epsilons just permuted. Okay. Right. Now I can extend actually a 0 to infinity to be a map from the affine Yangian of GL1 to an algebra generated by 1 over Z, and derivative with the standard relations, and given by the very same formulas. So Jn 1 over epsilon 1 Zn, but I now allow n to be arbitrary integral number, and h maps to epsilon 1, no 2. Okay, but now we have a coproduct delta going from this affine Yangian to the product of two of them, given by formulas J gets mapped to J times 1, Jn plus 1 times Jn, and H maps to H tensored with 1 plus 1 tensored with H plus sigma free sum over n equals 1 to infinity n J minus n minus 1 tensored with J n minus 1. These are exactly the same formulas that we used in our paper as well. Just written in this basis, but the same thing. And you can now take the coproduct. Okay, and how I define this A n1, n2, n3. I define it as a composition of n minus 1 coproducts with these elementary truncations of the form 1, 1, 0, n, and 1, tensored with A 0, 1, 0, and 2, tensored with A 0, 0, 1, and 3. And you can in particular do it for the two generators. Jn just gets mapped to this 1 over epsilon 1 I going from 1 to n1 z zi n plus 1 over epsilon 2 I from 1 to n2 z I n plus one more term, and H becomes the Kalugier-Moser Hamiltonian, or its free parametric generalization.
Yeah.
So it contains the following plus 3 terms of the following form, and then there will be terms like epsilon 1, epsilon 2 over epsilon 1, epsilon 3, sum over I j of zi, let me call this tilde, minus z tilde j, and a bunch of other terms of the following form.
So may I ask you a stupid question? So I somehow lost. This A and 1 and 2 and 3, well, it's a map. Yeah,
Yes.
But your algebra this A infinity, which belongs to W infinity.
So here I needed to extend in order to be able to use this coproduct. I had to extend the A infinity to the whole W infinity, or the affine Yangian, by including those negative powers.
Okay,
I need the negative powers in order to be able to define.
So which means that this it does not respect.
No.
Okay.
That's right. That's right. This is just like a useful way. What we are kind of able to curate with Davide by introducing some extra parameter and this holomorphic coproduct and all that. But I'm not sure if that is the best way to think about.
And how you use this coproduct? I mean, this kind of it does not look helpful in the representation theory, or it does, because you have highest weight modules and lowest weight. I mean, they do not like to be tensored. So how do you use this coproduct?
Right. Yeah, so in order to define these modules, so first we didn't really define with Davide the modules in terms of this description. So with Davide, we have defined only the modules for the universal algebra independently of the use of the coproduct. And we use the coproduct only to define the algebras A, N1, N2, N3. But we haven't established very well the relation between A, N1, N2, and N3 and the universal algebra. Well, I mean, we did, but like short answer, I don't really know how to use the coproduct to define the modules.
And these algebras, you need them for what purpose then? With 3 indices and 1, and if you used only universal thing.
Well, we do use them. We do use them, and we do define some modules for the algebra, but we don't define these modules using the coproduct, because like in the end, what you're going to get from these formulas. So this coproduct, what you can use this coproduct for is to give an argument that all these general A, N1, N2, and 3 are going to be representations of the affine Yangian. And this is basically the only way how we use the coproduct. Then whatever expressions we get, and we get the expressions of the following form, some kind of differential operators that contain possibly these singular terms. We can start constructing modules for these kind of algebras.
Oh, I see.
And this is what we do. But we, like, for the construction of the modules, we don't use the coproduct itself.
Yeah. Okay. So then, still in the center, this affine Yangian and whatever structures you have on them. Okay, on it. Okay, great. Now, the audience should understand that it's a discussion, so you are free to ask questions. So, are there any questions? And first of all, thank you very much for the interesting talk. Questions, please. Like, I don't know, maybe Zongzhu, he's the most.
Yes, I do have a question.
Okay, and why do
so the MPT from the character from this TTDT correspondence, the formula looks very much like a wild character formula. So the MPT, is that can you say that's irreducible?
Yes.
Denominator is the Markov. That looks like a Kurzweil denominator.
It does. Yeah. That's right. I mean, but I don't really have anything smart to say. So you're kind of asking whether it's a coincidence or whether there's a reason
because
for that?
at least the formula looks very much
Yeah.
The DT one, the M lambda mu looks like a Verma module. Okay, well, it actually should be the kind of a DGG resolution. Like the character formula looks better when you take the Euler characteristic. That's exactly what's the var character formula in the category O case.
Yeah.
So I didn't know if
that's a good point.
Yeah,
that's an interesting point. So Zhongzhu, you are saying that the conventional Weil character formula for Katz-Moody, it comes from localization theory on what, on the affine on the affine flag variety, probably.
well, because on the affine flag variety, that's another one which you take the higher cohomology groups of the corresponding vector bundles.
I mean that you can, because this formula, which on the slide, it has a geometric meaning, certainly, and the geometric meaning is very transparent. You take some toric, in general, toric Calabi-Yau threefold. Well, in this case, it's toric, but it's even more general. And so there are two types of counts. You count all, let me do not specify what does it mean count, although I can. You count all coherent sheaves with support of dimension less or equal than 1. This is DT count. It's Donaldson-Thomas theory. Or you can count the same coherent sheaves with no more than one-dimensional support, but such that the zero-dimensional part of it, like this sheaf, can have supported kind of zero dimension at points, but those points must belong to this one-dimensional portion. Or technically, you consider the moduli space of Pandharipande-Thomas stable pairs. It's like two-term complexes in the derived category of coherent sheaves. But anyway, it's naively, it's what does it say? And so then the generating function over all discrete invariants, which are basically like cohomology classes of the supported just a curve, something like element of H2, and the Euler characteristic of the sheaf, which is an integer n. So these generating functions are related exactly by the formula which is on the slide, that if you count just Pandharipande-Thomas, actually I'm not sure that it's written in the right way, but anyway, the generating function of all coherent sheaves with support of dimension no more than 1, and those which zero-dimensional part belongs to one-dimensional, they are related by dividing 1 by the power of McMahon function, and which means that intuitively speaking, if you allow if you do not bound the zero-dimensional part, it can be any collection of points which sits everywhere on your threefold, and the generating function of this zero-dimensional, of this torsion sheaf with zero-dimensional support, it's McMahon, essentially. It's some power of McMahon. So then if you prohibit them to live anywhere they want, then you should divide. And so then this how you get this PT generating function. And so then if you believe that this formula corresponds to relation between characters of some generalization of Kac-Moody, then it's indeed a character formula. And this is what Mira wrote. This is what on his slide. But the problem is that it's not about Lie algebras, because Kac-Moody, it's from the point of view of Calabi-Yau, it's related to two-dimensional Calabi-Yau categories. And we are talking about three-dimensional, which means that you, if you interpret the wild character formula in terms of the universal enveloping algebra, yeah, what is written here, it's can be. It's not kind of done in this generality. It should be related to the character formula for the cohomological whole algebra for your Calabi-Yau threefold, yeah, which is sort of a quantized version of the universal enveloping algebra. Yes, so then...
And that's exactly this McMuffin function in the var character formula. That is exactly...
Yeah, if, yes, again. So the point is that if you go from Calabi-Yau 2 to Calabi-Yau 3, then you replace Lie algebras by a more general object, which is not necessarily, well, at least kind of by construction, it's only an associative algebra. Then by complicated procedure, due to Davison and Meinhardt, you can construct a Lie algebra, which is called BPS Lie algebra. And Ben explained it to us in his lectures, in 3 lectures. Then this BPS Lie algebra probably admits some kind of a Weil character formula, and that's what's going on here. But nobody has done it. At least I don't know, because it's quite complicated to compute these BPS Lie algebras in pure geometric situation. Yeah, so that's, but it's a good question. Yeah, that's a good point. Yeah. All right. Sorry. More questions?
No more. Thank you.
Yeah. Okay. Maybe from other people. Well, if not, then Mira, thanks again for a nice talk. And yeah, we have your slides, and this is it. And
good. Okay.
Okay.
Thank you very much.
Okay. Be in touch.
Sure.